this video, we're going to explore limits and continuity. These are actually fairly complex topics, but the good news is that we only need to understand the basics for math methods. We will start by exploring what the limit is and the key scenarios that come up when solving limits. We will then look at continuity and see how we can use limits to prove if a function is continuous or not. Let's get into it. So, what is a limit? A limit seeks to explore how a function behaves as it approaches a specific number. The notation for a limit is as follows. Said out loud, this reads, the limit of f of x as x approaches a. For example, if f of x equals x plus 3, then the limit of f of x as x approaches 2 is 5. As x gets closer and closer to 2, f of x gets closer and closer to 5. Here's the thing. It's just as valid to go from smaller values of x to larger values of x as it is to go from large values of x down to smaller values of x. We differentiate between these two approaches by adding either a plus sign or a minus sign to the limit. A limit is said to exist if the limit as approached from the negative side is the same as the limit approached from the positive side. Let's look at a few examples which explore this idea. Suppose we wanted to find the limit of a quadratic function as x approaches 0. Well, from the negative side, we see that as x approaches 0, y also approaches 0. And from the positive side, it's the same story. This means that the limit of f of x as x approaches 0 exists, and its limit is 0. Now, let's try the same thing with a hyperbola. As we approach from the negative side, the curve approaches negative infinity. But if we approach from the positive side, we approach positive infinity. The negative and positive limits don't match. Hence, the limit of 1 divided by x as x approaches 0 does not exist. One more example. This time, let's look at the truncus. Approaching from the left gives us the same limit as if we were to approach from the right. The limit as x approaches 0 is infinity. This is an important distinction. The truncus still isn't defined for x equals 0. It still has an asymptote at x equals 0. But by using limits, we can see how the function is likely to behave at that point. This is one of the key uses of limits, observing how functions behave at asymptotes. Up until now, we've been looking at the case where the limit approaches a specific value. But how do we handle the case where the limit approaches infinity? There are a few properties worth mentioning first. Suppose we have a division of two polynomials. Each polynomial has a degree, or sometimes referred to as its order. The degree, or order, of a polynomial is its highest power. For example, this polynomial has a degree of 3 because 3 is its highest power. If the order of the numerator is smaller than the order of the denominator, then the limit as x approaches infinity is 0. If the degree of the numerator and denominator are equal, then the limit is finite and non-zero. Finally, if the order of the numerator is larger than that of the denominator, then the limit as x approaches infinity is either going to be positive or negative infinity. In all cases, we use the following process to find the limit. In this case, the denominator has a larger degree than the numerator, so we expect that the limit as x approaches infinity should be 0. Let's prove it. First, we want to divide the top and bottom of the fraction by the highest order term, which in this case is x squared. A neater way to write this division is to instead write it as a multiplication of x to the power of negative 2. We do this to prepare for the next step, which is to substitute x equals infinity. If we just left it as we had it earlier, if we substitute infinity into that, then we don't really know where to go from there. If we divide by the highest order term, then suddenly all these other terms are going to become fractions. If we substitute x equals infinity now, then all of those fractions are just going to go to 0. And since the entire numerator has gone to 0, this means the limit as x approaches infinity must also be 0, as we expected. In this case, the degree of the numerator is the same as that of the denominator. So we expect a finite, non-zero limit. So we'll divide by the highest order term and then substitute x equals infinity. After some simplification, we see that the limit of this polynomial as x approaches infinity is going to be 4. Finally, we look at the case where the numerator is higher order than that of the denominator. So we divide both sides by the highest order term and then substitute x equals infinity. In this case, we run into a divide by 0 error. The CAS will actually tell you that the result of this is going to be negative infinity because the numerator is negative. This isn't strictly true mathematically, but it is good enough for math methods. Now we can move on to continuity. In basic terms, a function is continuous if it's just one smooth curve with no breaks. Simply put, if a function doesn't have any vertical asymptotes or broken lines, then we can be fairly confident that it's going to be continuous. But let's dig a little deeper. There are three criteria for a function to be continuous. Firstly, a function can only be continuous if it's defined over its entire domain. This criteria is most often broken by functions like tan x, which have a domain that span multiple periods. Tan x is actually undefined at those vertical asymptotes, but the domain still includes them. This is one of the reasons why tan x is considered a discontinuous function. Secondly, the limit must exist for all points along the curve. That means that the limit as approached from the left must be the same as the limit as approached from the right. Lastly, the value of the function at a specific point must be the same as its limit at that point. Let's see what that means. This criteria is quite unlikely to be invalidated. Usually the first two are enough. But let's look at one example. The fact that I had to draw this one myself should tell you how rare this is. This piecewise function is defined at all points along its domain, so it passes the first criteria. The limit also exists at that point, because the limit as approached from the negative side is the same as approaching from the positive side. That's the second criteria met. However, the third criteria isn't met. The limit is not the same as the value of the function at that point. This function is discontinuous, and you could probably tell that just by looking at the graph. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge.